Welcome back, everyone. In this section, we'll be exploring continuous probability distributions. Specifically, we'll cover three important distributions: the uniform probability distribution, the normal probability distribution, and the exponential probability distribution. These distributions are crucial tools for modeling a wide range of business phenomena. Let's start by understanding the fundamental difference between discrete and continuous random variables in terms of probability computation. For discrete random variables, we use a probability mass function, denoted as fx, which gives us the probability that the random variable takes on a specific value. In contrast, for continuous random variables, we use a probability density function, also denoted as fx. However, it's crucial to note that the probability density function doesn't directly provide probabilities. Instead, we use it to compute the probability that the random variable falls within a certain interval. An important distinction to remember is that for continuous random variables, the probability of any single, specific value is zero. This concept might seem counterintuitive at first, but it's a key characteristic of continuous distributions. Let's begin with the uniform probability distribution. To illustrate this concept, consider an example of a random variable x representing the flight time of an airplane traveling from Chicago to New York. In a uniform distribution, every interval of a given length is equally likely to occur. This means that the probability of the flight lasting between, say, 120 to 130 minutes is the same as the probability of it lasting between 130 to 140 minutes, assuming these intervals are within the possible range of flight times. Now, let's look at Figure 4.17, which illustrates the uniform probability distribution for our flight time example. The graph shows a rectangular shape, which is characteristic of the uniform distribution. The horizontal axis represents the flight time in minutes, ranging from 120 to 140 minutes. The vertical axis represents the probability density. The flat line at the top indicates that all values within this range are equally likely. This visual representation helps us understand why it's called a uniform distribution. The probability density is uniform across the entire range of possible values. Figure 4.18 demonstrates how we calculate probabilities using the uniform distribution. In this case, we're looking at the probability of a flight time between 120 and 130 minutes. The probability is represented by the area under the graph between these 2 points. Because the distribution is uniform, this area forms a rectangle. The width of this rectangle is 10 minutes, from 120 to 130, and the height is determined by the probability density function. This visual helps us understand that in a uniform distribution, the probability of an event occurring within an interval is proportional to the width of that interval. The formula for cumulative probabilities in a uniform distribution: P of x less than or equal to x0 is x0 minus a divided by b minus a for x0 between a and b. This formula, 4.19, allows us to calculate the probability that a random variable x is less than or equal to a specific value x0, given that x follows a uniform distribution between a and b. Now, let's discuss some important points. For a uniform continuous probability distribution, we have a simple formula for the expected value: a plus b over 2. This formula gives us the average or mean value of the distribution, which is simply the midpoint between the minimum a and maximum b values. Now, let's move on to one of the most important and widely used probability distributions: the normal probability distribution. The normal distribution, often referred to as the bell curve due to its shape, has a wide variety of practical and business applications. It's used to model phenomena such as heights and weights of people, test scores, scientific measurements, uncertain quantities like product demand, rate of return for stocks and bonds, time required to manufacture a part or complete an activity. Its versatility makes it a crucial tool in business analytics and many other fields. Let's look at Figure 4.21, which illustrates the classic bell-shaped curve of the normal distribution. This symmetrical, bell-shaped curve is instantly recognizable. The highest point of the curve is at the center, representing the mean of the distribution. The curve tapers off symmetrically on both sides as we move away from the mean. This shape visually represents key properties of the normal distribution. It's symmetrical around the mean, The mean, median, and mode are all the same value, located at the peak of the curve. As we move further from the mean in either direction, the probability decreases, as shown by the declining height of the curve. Let's discuss some key characteristics of the normal distribution. Each normal distribution is defined by two parameters, the mean, mu, and the standard deviation, sigma. The highest point on the normal curve is at the mean, which is also the median and mode of the distribution. The mean of the distribution can be any numerical value, negative, 0, or positive. This flexibility allows the normal distribution to model a wide range of phenomena. Figure 4.22 illustrates three normal distributions with the same standard deviation but different means, mu equal to -10, 0, and 20. This graph shows how changing the mean shifts the entire distribution left or right without changing its shape. The curve with mu equal -10 is centered at -10 on the x-axis. The one with mu equal to 0 is centered at 0, and the one with mu equal to 20 is centered at 20. This visual helps us understand how the mean determines the central location of the distribution, while the shape remains consistent when only the mean is changed. Continuing with the characteristics of the normal distribution. The normal distribution is symmetric. The shape of the curve to the left of the mean is a mirror image of the shape to the right of the mean. The standard deviation determines how flat and wide the normal curve is. Larger values of the standard deviation result in wider, flatter curves, indicating more variability in the data. Figure 4.23 shows two normal distributions with the same mean but different standard deviations, sigma equal to 5 and 10, respectively. This graph illustrates how the standard deviation affects the shape of the distribution. The curve with sigma equal to 5 is taller and narrower, while the curve with sigma equal to 10 is shorter and wider. This visual representation helps us understand that a larger standard deviation indicates more spread in the data, resulting in a flatter, wider curve. In our ongoing discussion of the normal distribution, we have one more crucial characteristic to explore: probabilities and areas under the curve. Probabilities for the normal random variable are represented by areas under the normal curve. It's important to note that the total area under the curve for any normal distribution is always 1. This is a fundamental property of probability distributions. Due to the symmetry of the normal distribution, we can make two key observations. The area under the curve to the left of the mean is exactly 0.50 or 50%. Similarly, the area to the right of the mean is also 0.50 or 50%. This symmetry is crucial for understanding and calculating probabilities in normal distributions. Now, let's apply the normal probability distribution to a real-world scenario. We'll look at Greer Aircraft Engines, a company that sells engines to commercial airlines. Greer offers a performance-based sales contract, guaranteeing that their engines will provide a certain number of lifetime flight hours, provided the airline purchases a preventive maintenance service plan. Based on extensive flight testing and computer simulations, Greer has determined that the mean lifetime flight hours for their engines is normally distributed with mean mu equals to 36,500 hours. Standard deviation sigma equal to 5,000 hours. Let's consider this question. What is the probability that an engine will last more than 40,000 hours? Figure 4.26 shows how we can use Excel to calculate this probability. Using the norm.dist function in Excel, we can calculate that the probability of an engine lasting more than 40,000 hours is approximately 0.2420 or 24.2%. This means that about 24.2% of Greer's engines are expected to last more than 40,000 hours, which is valuable information for both Greer and their customers. Now, let's consider two more scenarios. Greer is thinking about offering a guarantee that provides a discount on a replacement engine if the original engine doesn't meet the lifetime flight hour guarantee. How many lifetime flight hours should Greer guarantee if they want no more than 10% of aircraft engines to be eligible for this discount? How do we calculate the probability that an engine will have a lifetime of flight hours greater than 30,000 but less than 40,000 hours? These questions demonstrate how we can use the normal distribution to make important business decisions and calculate probabilities for specific ranges. Figure 4.29 shows how to use Excel to find the probability that an engine will last between 30,000 and 40,000 hours. By using the norm.dist function twice and subtracting the results, We can calculate that the probability of an engine lasting between 30,000 and 40,000 hours is approximately 0.7257 or 72.57%. This high probability suggests that a large proportion of Greer's engines fall within this range, which could be useful information for maintenance scheduling and warranty planning. Now, let's move on to our final distribution, the exponential probability distribution. The exponential distribution is often used to model random variables such as time between patient arrivals at an emergency room, distance between major defects in a highway, time until default in certain credit risk models. This distribution is particularly useful for modeling the time between events that occur continuously and independently at a constant average rate. Let's consider an example where X represents the time between business loan defaults for a particular lending agency. If the mean time between loan defaults is 15 months, we can graph the probability density function as shown in Figure 4.30. The graph shows a curve that starts high and decreases rapidly, then tapers off as X increases. This shape is characteristic of the exponential distribution and reflects the fact that shorter times between events, in this case, loan defaults, are more likely than longer times. To compute exponential probabilities, we use a specific formula involving the mean of the distribution. Excel provides the expand.dist function to make these calculations easier. Figure 4.31 demonstrates how to use Excel to calculate the probability of a time between loan defaults falling between 6 and 18 months. By using the expand.dist function twice and subtracting the results, we can find this probability. This type of calculation is crucial for risk assessment in financial institutions. In conclusion, we've covered three important continuous probability distributions: uniform, normal, and exponential. Each has its unique characteristics and applications in business analytics. Understanding these distributions and how to work with them is crucial for making data-driven decisions in various business scenarios.